Have you ever wondered what really allows you to send a message or even money to someone on the other side of the world without a bank or some big tech company sitting in the middle? Well, the answer is one of the most important technologies of our digital age, cryptography. It is the silent guardian of our entire online world, and today we're going to crack the code on how it all works.
Welcome to CodeAccessHub. We're all about making the complex tech that shapes our lives really simple and clear. So let's get right into it.
I want you to just picture this for a second. You need to send something valuable to a total stranger online. But here's the catch. There's no bank, no PayPal, no one in the middle to guarantee the transaction. How on earth do you trust them? How do you know for sure that the exchange is secure? This, right here, is the fundamental problem of digital trust.
And that huge problem of digital trust? Well, that's exactly what we're tackling today. And the hero of our story, the really elegant solution that makes amazing systems like blockchain even possible, is cryptography.
So, what exactly is cryptography? At its heart, it's the science of secure communication. It uses some seriously clever math to create a system where we can have secure, pseudonymous, and trustless interactions. You can think of it as the mathematical rulebook that lets strangers play fair and transact safely, no middleman needed. Now, the power of cryptography really stands on four key promises, or pillars. First, confidentiality. This just means your message is private. Then there's integrity. This proves your data hasn't been messed with. Third is authentication, which confirms everyone is who they say they are. And finally, non-repudiation, which is like an unbreakable digital signature. Together, these four pillars build an absolute fortress of digital trust.
So, to deliver on all these promises, cryptography uses a pretty powerful toolkit. We're about to pop the hood and explore the three core components that make the blockchain tick: symmetric keys, asymmetric keys, and these incredibly clever things called hash functions.
Okay, first up, keys. These are the secret codes that lock and unlock our data. With symmetric encryption, you use just one single shared key to do both jobs. It's super fast, but you've got this problem of how to share that key securely in the first place. Asymmetric encryption solves this with a brilliant pair of keys, a public one for locking and a private one for unlocking. It's a bit slower, but way safer for open networks. In fact, they're often used together. You use the slow, safe asymmetric keys to securely share a fast symmetric key. Best of both worlds.
For a super simple example of a symmetric key, look no further than the ancient Caesar cipher. The key is just a simple rule: shift every letter forward by 3. So hello becomes coor. Both the sender and the receiver have to know that same secret rule to encrypt and decrypt the message. It's basic, I know, but it perfectly illustrates that core idea of a single shared secret.
Asymmetric keys, though, are the absolute bedrock of cryptocurrency. The best way to think about it is like a secure mailbox. Bob has a public address, his public key, that anyone, like Alice, can use to drop an encrypted message in. But only Bob has the private key to actually unlock that mailbox. So if some eavesdropper, Eve, intercepts the message, it's just total gibberish to her. This is exactly how your crypto wallet works. Anyone can send you coins using your public address, but only you can access them with your private key. All right, on to our third and final tool, the hash function. And honestly, this is one of the most ingenious concepts in all of computer science. You can feed any data into it, a single word, a picture, the entire Library of Congress, anything, and it spits out a unique fixed-length code. It's like a digital fingerprint for that specific data. And here's the crucial part. It's a one-way street. You can never get the original data back from its fingerprint. So what makes these digital fingerprints so incredibly secure? Well, it comes down to four key properties. They're deterministic, meaning the same input will always give you the same hash. They're pre-image resistant, which means you can't reverse the process. They produce a fixed length output, no matter how big the input was. And maybe most importantly, they have what's called the Avalanche Effect. If you change just a single comma in an entire novel, the resulting hash will be completely unrecognizably different. This extreme sensitivity is what makes them perfect for spotting any tampering. So, we've got our toolkit. Asymmetric keys for identity, and hash functions for integrity. Now for the big question, how do these pieces come together to actually build the blockchain? Let's see how this unbreakable chain gets forged.
Okay, this is where all the magic happens. Every single block of transactions gets run through a hash function, creating its own unique digital fingerprint. Then, and this is the key, that fingerprint is literally embedded inside the next block in the sequence. This creates a cryptographic chain, linking each block to the one before it. Now, if a hacker tries to alter a single transaction in a past block, its hash will instantly change, which breaks the entire chain for everyone to see. It becomes practically impossible to cheat the system.
You might be wondering, but what about the hundreds of transactions inside a single block? How are they all secured? Well, that's the job of something called a Merkle tree. It's a really clever data structure that hashes transactions in pairs, then hashes those resulting hashes together, and keeps doing that until only one single Merkle root hash is left. This one fingerprint, placed in the block header, is all you need to efficiently prove that every single transaction below it is completely unaltered. It's genius.
So let's do a quick recap. Hashes secure the chain itself by linking all the blocks together. Digital signatures, which use our private keys, are what authorize transactions and prove ownership. Proof of work is basically a massive hash puzzle, where miners race to find a specific hash that secures the whole network. And finally, Merkle trees make sure all the data inside those blocks has total integrity. You can see cryptography is literally woven into every single layer of the blockchain.
But, the story doesn't end here. The world of cryptography is always evolving, always facing new challenges and pushing toward the next great frontier in security.
One of blockchain's biggest ongoing challenges is this constant balancing act between speed and security. Sure, you can make blocks bigger or faster to process more transactions, but that makes it harder for regular people to run a node, which can lead to centralization. And once you have centralization, you open up a whole new can of worms when it comes to security risks. Finding that perfect balance is one of the toughest engineering challenges in the space. And looking out on the horizon, there is a massive threat looming: quantum computing. These incredibly powerful computers of the future could, theoretically, be powerful enough to break the asymmetric encryption that protects all of our private keys today. Now, this is a long-term risk, but it's one the crypto world is taking very, very seriously. The good news is, the race is already on to develop quantum-resistant algorithms. Researchers are exploring completely new types of math, based on super complex problems in areas like lattices and multivariate equations that are believed to be secure even from a quantum computer. The goal here is to future-proof the entire ecosystem before the threat even arrives. All right, we've covered a lot of ground. Let's boil it all down to the most important takeaways from our journey today. So, what's the bottom line? First, cryptography is what solves that fundamental problem of digital trust. Second, asymmetric keys give us secure digital identities that let us transact with strangers. Third, hash functions create those tamper-proof fingerprints for our data. Together, these tools build the blockchain's unchangeable, transparent ledger. And, looking ahead, the next big frontier is building defenses for the quantum era. And that kind of leads me to a final thought for you. As we move deeper and deeper into a digital-first world, just think about it. What system in your life, whether it's voting, property records, or even your personal identity, do you wish had the same unbreakable, transparent trust that cryptography provides? I really hope this helped you get a solid grip on the cryptographic backbone of the blockchain. For more explainers on the tech that's shaping our future, make sure you subscribe to CodeAccessHub. Thanks so much for watching.